with other variables. So all I'm going to do, so right now we've been dealing with y as a function of x, is traditional notation. Now, one of the things I always have problems with is that um, because of the way a lot of teachers teach material, every single thing that is covered is y equals f of x, y equals f of x, or y is a function of x. One of them, they don't teach function notation that well in the early years and building up. So there's a lot of issues that students have with function notation. But the other thing is it's always y as a function of x. This does not need to be the case. So this is the dependent, and then we have the independent variables. And it's going to be the same. But in today's work, for today's, I'm going to switch it up. Okay. So we might, so when we have this dy dx, it's also noted that we're taking a derivative of y with respect to x. We take the derivative of the dependent variable with respect to the independent variable. And that's why we have this dy dx. That's what it really means. And actually, let me just write that notation a little bit clearer. It's d dx of the function y, which is dy dx. So in today's material, we might have x as a function of y. We might want to know, how does x change in relationship to the y variable? And as such, we might want to find dx dy. The rate, and I want to actually write this. When we think about this in the others, this is the rate at which x changes when y increases by 1 unit. And that's going to actually play an important role in Monday's lesson, dx dy, the concept of dx dy. I'll get into that on Monday. We might have a very traditional one that we're talking about is x is a function of t. So we might want to find dx dt in that problem. And typically that deals with the left and right movement with respect to time. As once we finish the function type of material in relationship to derivatives, we're going to get more conceptualized and application. And those applications traditionally deal with motion and rates of change. We might just want to use the context of the problem, something like height and width. So h might be a function of w. We're going to work with more the transcendental functions and especially the sinusoids. Now, in these first lessons of what we've been doing, I have not put on any problems that have to deal with sine, cosine, exponential, or logarithmic. At the end of this unit, that's what we're going to focus on. We're going to do everything pretty much that we've done with those type of functions. Right now, I'm really working on you understanding the process of how we do these problems, which are the most important problems that you'll do with this topic. But we also need to be comfortable with some transcendental type functions. So with trig, we usually say r, the radius, is a function of theta. The angle made from the x-axis to the line. I didn't say that this is dh dw, and then this would be dr d theta. The work is the same, all right? So the key aspect here is that if differentiating with respect to a different variable, don't forget the chain rule. D, is attached. So if the variable is the same, then you don't got anything that works. I see someone with the annotation. I have the annotation feature on. If you could just turn it off. I mainly keep the annotation part there for office hours, and I just didn't bother to turn it off. So we can just keep that off though. I feel that with calculus, I don't have to turn it on and off all the time, so I just kept it on. So if differentiating with respect to a different variable, chain rule, there's always a d variable is attached. So what do I mean by that? Well, i.e., the derivative of a squared with respect to a is what? What is the derivative of a squared with respect to a? Can I get someone that would say what the answer is here? So a is my variable. 2a, yeah. But what is d a squared with respect to b? What's the derivative of a squared with respect to b? So now we're taking derivative with respect to a different variable.
2a?
Almost. Now, in this first example, we really have it's 2a dA, the derivative of a with respect to a. But the derivative of a with respect to a is 1, right? At what rate does a change when a increases by 1? Well, if a increases by 1, then a increases by 1. So the rate of a with respect to a is 1, and that's why we get that 2a over here. You just didn't really do it. But over here, it's 2a times dA dB. And we don't know what dA dB is, and so my answer is 2a dA dB. So that's going to be the hardest part when you're dealing with today's problem. But that really doesn't have to do with calculus. It's just that it's the same thing. If it was y, if we were taking derivative with x with respect to x, we didn't have any like chain rule piece that was connected to it. You could write dx, but the derivative of x with respect to x is 1. So every time you do that, you're just multiplying by 1, which we don't show. But when we took the derivative of something with y squared, y cubed, or just y, then we always had a dy dx attached to it, because then we have to multiply by the derivative of y with respect to x. So it's the same thing. Now, I'll answer it now. No, you can't just change every x to y and y to x and then try to change it back at the end. That defeats the purpose. That just defeats the purpose, but then it defeats the purpose of what I'm trying to have you understand and do. So don't try to. You can do it to check your work after the fact if you want to, but it's not. You need to get comfortable working with variables that are not x and y. My very first year teaching AP Calculus, I made the mistake of not focusing and doing any problems with non-X and Y, and it ended up eating the class alive on the AP exam because there was like two major problems that didn't have Y with respect to X, and the class was like, "We've never did a problem like that. You never taught us how to do those type of problems." And I was like, "Well, it's the same thing, but unless I explicitly show you and almost explicitly have a lesson for it at least once right now, um, you feel like it's a whole different thing, but it's not." So, example. A squared c cubed minus 2c equals 5. Find dA dc. Okay. Now, this technically is the same type of problems that you've been doing. A is your dependent variable. It says so what this notation says is that A is the dependent variable and C is my independent variable. So A is like Y and C is like X. And so as Farida has saying here, the first thing we're going to do is the product rule. So we want to differentiate. If we want to find dA a derivative, then we need to differentiate. So perfect. Product rule. Okay, so we're going to do product rule here. And then this will be my U and this will be my V. All right, so what product rule looks like this? I like to write my product rule like there. It just helps me, brackets and parentheses, set them up. All right, now I added this extra parentheses on the outside here, and that's more just for the organizational piece. It doesn't really matter here, but sometimes if you're doing a product rule where it's a minus and then a product rule, that can help. So this is just an organization feature. All right, what do I get?
Um, 2A divided by C3 to the third power.
No.
Isn't it U prime V?
Yeah, so what's U prime?
Yeah, U prime is 2A.
No.
Oh, times dA over dC.
Yeah. I think I'm just gonna give up on the over part. But yeah, so we're taking it with respect to a different dA. We're finding a derivative with respect to C. So if it's anything that's not C, we have to have that dAdC attached. All right, so you always have to be looking on the lookout for dAdC. All right, times. I think you said it correctly. Times what?
C to the third power.
C to the third power, good. Plus
3C to the second power.
good.
And A to the second power.
Good. I have some students that will always write like 3c squared times dc dc, so they'll write like the times dc dc, so that they understand and they're like, oh, okay, so that doesn't really matter. You don't have to show that part, but some people need it in terms of their part. Minus 2
equals 0.
Perfect. So clean this up. 2ac cubed dAdc plus 3a squared c squared equals 2. Move that minus 2 to the right hand side. I like to clean it up, and I like to leave my coefficients in the front and then utilize the letters. So A before C, just to make it look a little bit cleaner, and putting my derivative piece at the end. These are just organizational thought processes that go on in my head that I think they're very helpful when cleaning up problems and making you feel a little bit more comfortable to do the rest of the algebraic work.
Mr. G,
Yeah.
you moved me
Okay, where?
at the 2a times dA over dc.
Okay.
Why did you do?
It's the same exact thing that I actually put that example right back here. So I didn't hear the question coming from here. So we got to go back to this part of the notes. So if when we took the derivative of a squared with respect to b, now instead of b, it's just c. So it's the same idea here. When I took the derivative of a squared, a with respect to a, I get a dA, which is just 1. So that's why I just get a normal 2a. But if I take the derivative of a with respect to b, then I get the 2a times the derivative of a with respect to b. It's just chain rule. We're still doing a chain rule here. You're always technically doing a chain rule. But if you're taking the derivative with respect to the same variable, then the chain rule just gives you 1. But if we take the derivative with respect to a different variable, then we don't get 1, we get dA, we get that derivative, we get the chain rule. This is the chain rule right here. So this is chain rule, this is the chain rule. However, we traditionally don't show this type of chain rule because it's just 1 when we take the derivative with respect to the same variable. So the same thing happened here. It was 2a times the derivative of a with respect to c. And over here, as I said, this was 3c squared times, and I had written it earlier, it's dc. But it's just 3c squared times 1. And we traditionally just don't write that times 1 because we're taking the derivative with respect to c.
Okay.
It's the same thing. I could have written this problem as y squared x cubed minus 2x equals 5. This is the same exact problem. And like I said, I find this to be a product of how you have students that have learned their material and their algebra in the early grade levels, building up to calculus, and not doing, and every problem had to look like x's and y's, and not branching out to different letters, because in reality, it's all x and y are unless you're talking specifically about particle motion, all x and y are just randomly chosen variables. Why is it the x-axis and why is it the y-axis? Because someone said it. Why isn't it the a-axis and the b-axis? Like, one person decided that that's the variable we were going to use, x and y, and x for an unknown. And actually, the x for the unknown comes from some. There's a history behind why it's x is always used. It's just a language thing in terms of. I've learned it one time. I don't know which country, but the letter X, it comes from the value unknown inside some language that of whoever who was developing the math, and that's it. So it could have been the A variable and the C variable, and that's what every student could have been using since the dawn of time. But no, it was X and Y. So that's it. All right, what do I do next?
Would you minus the 3a squared c squared to the other
Correct.
side?
So 3ac cubed dAdc equals 2 minus 3a squared c squared. Perfect.
And then you divide your 2ac3 to both sides.
So dAdc equals 2 minus 3a squared c squared all over 2ac cubed. And that is my answer. New example. S squared R equals 4. Find dr ds evaluated when R equals 1. Okay. Where do I want to start? There's two places that we can start in doing this problem. It literally doesn't matter which one we do first.
We can do the derivative.
Okay, we can do the derivative. So let's differentiate. All right, well, if I differentiate, what do I get?
2s multiplied by dr. Oh no, why not? Oh, product. Okay, that makes more sense. Okay, multiplied by r plus dr ds multiplied by s to the second power equals 0.
Okay. What do I do now?
Plug in for 1.
Plug in R equals 1. But what's wrong?
I don't get it.
Can someone...
Does it have to be some type of... Oh wait, I was gonna say... Oh, no, never mind.
Speak your minds. Let's do... What is that?
What did you ask?
What do I do next?
Oh. Okay, would you just move the negative of the 2SR to the other side?
You could do that, but I want to be more efficient in terms of our thinking.
Mister, I thought it was equal to 4.
Oh, no. Big. We said that is the number. When I first taught this subject, I said that is the most common mistake that people make.
It's a variable.
No, 4 is not a variable. What's the derivative of 4?
Nothing. I don't know what that's called, but I understand.
It's 0. The derivative of 4 is 0.
Yeah. Do you want us to factor?
No. Let's see. Let's go with Frida. What Frida said. So 2s times 1 plus dr ds times s squared equals 0. What's wrong? Same thing that we did yesterday. This is a problem that pretty much I covered yesterday.
2s is on the wrong side?
No. No. Now, yeah, we are going to need the drds by itself. But the question here is that in an implicit differentiation, we also need to know what's s. Remember when we had to find the derivative problems, and I said find the derivative when x equals 1? And then, in the notes yesterday, I explicitly found what y was, and I made that its own problem. But you don't always have to. So we need to figure out what is the s value. And this is what I was going to say. We could have started by doing that. If I know r is 1, with implicit differentiation, I want to know...
We could just start to the original equation.
Correct.
Just plug in 1 for r.
So whenever we do implicit differentiation problems and we need to plug in, we always need both values. Whenever we're doing this idea of plugging in, always just be like, I need to know both R and S. So good. So Ariana had said, I'll use the S squared R equals 4, giving me S squared 1 equals 4, giving me S squared equals 4. So S is equal to?
2.
No.
Not 2.
I wouldn't give you credit, full credit.
Plus and minus 2.
Plus or minus 2. So now we have R equals 1, S equals negative 2. And we have R equals 1, S equals 2. Ah, so this is actually a two-part problem right here. There's going to be two answers to my problem. So we'll also deal with when S equals negative 2, and we'll deal with when S equals positive 2. Now, if I had done this in the beginning and I realized this, I would have broken it. I would have gone right here and done them like this traditionally, right? But sometimes, because remember, we need to understand that when this question is asked, the answer is a expression. The answer is a value. If I just ask you to find dr ds, then my answer will be an equation. So that understanding the difference between an equation answer and an expression answer is very important. My answer is not going to have r's or s's in it. My answer is going to be a number. So a lot of you were trying to do this work, but your answer was going to be in terms of s and r, or just s. We need to recognize that the answer here is going to be a value. So all right, so if I do that, there's two problems here. So that's going to give me, if I plug in s equals negative 2 here, that gives me negative 4 plus 4 dr ds equals 0. 4 dr ds equals 4. Okay, so then dr ds is equal to 1. And this is for when r equals 1, s equals negative 2, just to make sure I explicitly say that. You can use the evaluation symbol if you wish to. Hey, get back here, don't do. And over here, if I plug in 2, I get positive 4 plus positive 4 dr ds equals 0. Okay, so dr, and I can see that math. I don't have to show all my steps in terms of it. I can clearly see that dr ds will be negative 1. And so that's my other answer when r is 1 and s is 2. So I have two answers here. That was one thing. You're going to have problems on your homework again tonight where you're going to have multiple answers. And you need to recognize that my answer, as you can clearly see now, my answer is a value for this problem. Now, for the purposes of lecture, I want to make sure that I do the most efficient way. And so if you are a student that feels that you always want to find DRDS and then you plug in, you can do that. But the majority of the time you're doing more work, or you're doing more steps, or you're doing things that will lead to more mistakes. Doesn't mean you will make a mistake. Doesn't mean you're not doing it wrong either. It's just that you're more prone to it's easier. Even when I do it, it's much easier for me to make a mistake if I try to solve for it. Find the equations of the tangents to problem above. Okay, so tangent lines. All right, now this kind of also throws people off because they're like, well, why tangent lines can only be y equals mx plus b. Now that was a lot of people at the beginning of the school, right? People were like, tangent lines always have to be written as y equals mx plus b. False. We learned that very quickly. Tangent lines, y minus f of a equals f prime of a, parentheses x minus a, is a perfectly fine way of writing a tangent line. But now we're going to add in the fact that it doesn't need to be a function y as a function of x. So R is my dependent variable. So R is like the Y, S is like the X. So what is my equation going to look like? Do not tell me Y.
R minus 1.
I just said do not tell me Y.
Want the original equation?
No, how do we write the equation of a tangent line? How's my answers going to look? Using the letters R and S.
R minus 1 equals
R is my independent variable, so it's R minus F of 1.
equals.
Oh, sorry, it's not even F of 1. It's, yeah, you're right. Y minus 1 equals
And then we could do 1.
R prime times S minus. So there's going to be two equations here. Let me just write it this way. Let's do this first one. R equals 1, S equals negative 2, dr ds equals 1. Okay, that's the first one. The other one is R equals 1, S equals positive 2, dr ds equals negative 1. So now that we have this information, we're just going to go directly to the answer. So I heard R minus 1 equals 1 parentheses
S plus 2 parentheses.
Done. This is like my Y, okay? Because it was dr ds, so this is like my Y. And once you connect one of them, you can just rewrite it as such. So my other one is R minus
1
equals
negative 1
parentheses,
X minus 2.
and there we go. You just wrote a tangent line, and really it's not necessarily a tangent line. We refer to these as relationships, as linear relationships. When we take things like statistics, it's a relationship between R and S, and it's a linear relationship that we have between these two. So we're trying to relate S to R. So it's just another variable. I want to note that everything that we've done today, everything that we've actually done is technically nothing new in terms of the processes, in terms of the steps. The only hard part here is to understand, and this is why, and I was trying to drive home earlier on, whenever we were doing these derivatives, it was the derivative of y with respect to x. So we're asking, how much is y changing when x increases by 1 unit? That's what the derivative means. If the x increases by 1 unit, how much is y changing by? That's what slope is. That's the definition of slope. The change in y when x increases by 1 unit. So what we're asking here is how much does r change when s increases by 1 unit? And the first part, it's 1. That's 1 to 1. When 1 goes up 1, the other one goes up by 1. And the other one is negative 1. When s increases by 1, r decreases by 1. So that's what I have for you. I'm going to keep it there. We have a homework handout. It's been posted for you. Like I said, it has a lot of reviews, so don't worry. Not the entire homework isn't just X's, A's and B's and R's and S's and stuff like that. I think only like a quarter or a third of the homework is like that. The majority of your homework is just going to be review from what we've previously done, because I want to make sure that you master that. This topic comes back. This idea of implicit functions and differentiation does come back later on. We are not done with it, but I need you to be very strong with this differentiation when we move into Mondays. Because when we move into Mondays, the concepts are going to be a little bit trickier. The math might be a little bit trickier. So I almost want today's kind of almost meant as a review day of getting some extra practice, rather than me just chugging along with really new material. But it's good to have these conversations about different variables. It's not like I say, it's not a calculus topic. It's not a calculus concept. It's just a math algebra concept of different variables that I feel is very important. We'll end class a little early today because I always keep you on the asynchronous days anyways. So it's 8:52, 13 minutes left. Go off, do your homework. Have a good weekend, everybody.